Hello ladies and gentlemen, welcome to another thing where I talk about things. Today, another episode in the suit, because this is actually a more formal episode. I was commissioned to do this. A guy offered me some amount of money for a commission to talk about this kind of video, and he wanted to know about statistics. He wanted me to talk about how we apply it, how it's relevant to research, how it's relevant to the world in general. And especially because after my psychology in overview video, I spoke somewhat disparagingly about statistics, because a lot of times they're not applied very well, and people don't really realize that they can be very complex. I mean, especially when you see research done by people in fields, and their fields don't require, like, calculus, or something like that. Like, if you get a researcher who doesn't know calculus, you basically have a researcher who shouldn't be using statistics at all, because statistics they're very heavily calculus-based. You get into a lot of factorials and Taylor series equations and things like that, because it's rather complex, and we are going to discuss that complexity today. So, starting off, I'll talk about some of the things that we actually use statistics in. Business is a big deal. Business is a very prominent user of statistics. They like to gather all kinds of data for a lot of different things. One good example would be quality of a product. Like suppose, for example, you own a light bulb factory and you're going to be selling light bulbs. You need to ship out like 1 million of these things per day. I don't know if that's realistic, but let's say it's a multinational light bulb company, and it just sends out millions of these light bulbs every single day. Well, what they're going to do then is they're going to hire some kind of expert in their field, probably like an engineer or someone. It tends not to be a statistician actually directly, because statisticians they tend, I think, to be more confined to fields of research. They're often ones doing studies to kind of pick stuff out. It depends a bit, but a lot of times for product quality, you'd have like an engineer who'd do this sort of thing. And you go through and you test every single one of these. You think that they can't test every single one of the light bulbs. There's too many light bulbs. There's millions of them going out every day. It would delay your shipments. You can't look at them all. So what you do is you get about 100 light bulbs, and you test them, and you see how many of the light bulbs come back faulty. Ideally, it would be none, but that's not realistic. So out of those 100 light bulbs, you find that maybe like 2 of those 100 light bulbs don't work. So the question now is, how do we take that data, this small sample of 100 light bulbs, and apply it to our large sample of 1 million light bulbs? And you may notice right away that this is kind of similar to doing research on people. Like if you have a small group of about 100 people, and there's a population of 300 million, then how do you extrapolate this data about 100 people into a population of 300 million? So this is very common. It tends to be you get small samples and you're trying to figure out how to apply the data to a large sample. Now, it feels like you should be able to just say that if 2 out of 100 light bulbs are broken, then in theory 2% of the light bulbs are broken. That's what you'd think. But actually you'd be wrong. Statistics is a bit more complicated than this, because as it turns out, there's a certain probability that maybe you grabbed every defective light bulb in the batch of 1 million light bulbs, and you just managed to get so unlucky that those 2 broken light bulbs out of the millions that you could have chosen from happen to be in your test batch. So another part of statistics is figuring out the odds of really everything involved, all of your variables. You've got to actually sit down and you look at, your data, and you say, so I chose 100 I chose 100 light bulbs randomly. What are the odds in the first place that I would even get 2 of these light bulbs? Like if there were a certain percentage of light bulbs that were broken, what are the odds that 2 of them out of this 100 would be broken? So you actually go back and you look at a lot of variables, and they use much more complex math than just this 2% number to figure out whether or not they really have a bunch of defective light bulbs or not. Because 2% out of 1 million, that's actually a really high number. You don't want that. But odds are not terrible that you would, just from a random sample of 100, pick out 2 defective light bulbs. So that's kind of what they get into. They sort of look at like, is this number adequate enough? One of the biggest things is determining, not just looking at the simple numbers, but figuring out further what the numbers mean. We'll get into that later. I'll continue to talk about things that we use them for. But anyway, another thing in business that's very important is this concept of technical analysis. And technical analysts, what they do is they look for trends in marketing. They look for things that are popular. Like if they're a car dealer, they look at the car colors and they say like, nobody's buying purple cars, but everyone's buying black or red cars or whatever. Those are popular right now. I don't think that red cars are all that popular, but black, let's say black cars are really popular, and they sort of look into that, and they see that they've got a higher number of cars, statistically speaking, that are being purchased and they're black. And so that's, it's simpler market research. It's a little bit less complex than quality assurance at times. It depends on what you're trying to look at. But this is the same thing, though. You do still get into, like, you have a small sample group. You look at this data that you get from, like, a few retailers or just places that are contributing this data, and you try to extrapolate it out to a larger population, which is always the hardest part. And then we get into epidemiology. Epidemiology is also another area. This is more in research than it is in business. But more specifically, it actually has to do with medicine most of the time. Good epidemiology does. Epidemiology is when you know the cause of something. Like, for example, if there's a big outbreak of Campylobacter, like that's a food poisoning kind of bacteria. If everybody's like suddenly coming down with Campylobacter, and this actually happened to me once. I got Campylobacter while I was in Germany with Kenza, and when I came home, they discovered it and they treated it, but then I got a call from like a health administration, like one of the state-run health administrations, and they were like, "Where did you get this from?" Because they were trying to figure out if there was any other cases of this of the bacteria getting into people's guts. Where was it coming from? That's epidemiology. They kind of look around and they talk to people and they say like, "Where did you eat? Where'd you get your water?" And then based on if they find a common thing, like 100, like if they talk to 100 people and like 90 of them say that they drank water from this one place, this one center of distribution, like a particular well, then that's probably where your Campylobacter is coming from. And then they send out a researcher to go and examine the water. Like he'll go and he'll find the Campylobacter in the water and he'll say, "Yep, there it is. This is what we're doing." So epidemiology, not a conclusion, just a way to point people in the right direction so we can actually make conclusions. And like I say, this is actually, even in business and marketing, when we talk about like how much of our product is broken, it's not like they don't do the test and then find 2 light bulbs and say, okay, 2% of the light bulbs are screwed up out of this 100. They actually just kind of say, these are the odds that you've got this many defective light bulbs, and if that's okay with you, then that's okay. But if not, you might want to look into it. Maybe you want to do a recall. It tends to be that what they'll do is they'll look at their product and they'll try and figure out, like, do we have a higher incidence of failure? Is there something that we need to look at? And if they can't identify anything, then they tend to just let it go, because it's like there's nothing really, it could just be a fluke of the numbers. We don't know what it is. So that's statistics in the applied world. We also get that in research. Research tends to be somewhat similar, but oftentimes misapplied. You'll find that in research there's a couple different kinds of data that are reliable. There's case studies. Case studies are the weakest option available to you. That's like stories, personal tales of things that happened. Like if you just talk to a guy and he goes, "Oh yeah, I got a Campylobacter poisoning, and I was eating at the local Mexican restaurant." That's a case study, and that guy may be wrong. He may not have gotten his poisoning from the Mexican restaurant. He just thinks he does. So very unreliable, but it can give you a point to kind of start and to maybe start asking questions. But very weak still. Statistical data then is your next strongest sort of data, and that's when you start to look at, like I say, some numbers, and then you try and figure out what are the odds that my numbers are completely ruined, because a lot of times they are very much false. These numbers, like I say, they're more to direct people towards actual research. Like if you get numbers, if you get statistics, and they say that you've got Campylobacter in this one place, like I say, then you send a real researcher, and he does an actual study. Then you have actual empirical data. Actual empirical data is always your strongest thing. That's when someone actually examines your product or your wells or whatever it is that you're looking into, and they determine whether or not you've got a problem. Or they try to figure out what the problem is. Now, what you guys will find very often when you follow researchers, especially if you follow like highly ideological researchers, or if you look into like research that's very politically charged, you'll find a lot of people who use statistics to kind of game the system. There are a lot of things in statistics that you need to look out for and that they teach you about in a basic statistics class. This is one reason why I said that when I talked about some stuff, like some of the there's a lot of alarmism in feminism when they talk about like 50% of women are going to be abused, or 90% of men are rapists, or this or that. Those are all like statistics, and they don't really mean anything. And the reason why they don't is because of how the numbers actually work. When you gather that data, a lot of times what they want to do is they look at what's called a standard deviation. And a standard deviation doesn't actually mean anything specifically unless you know what it is that you're looking at. But basically it's a deviation from an expected value. Like I say, suppose you're looking at car sales, and for some reason people really like black cars. So if you're just looking at the average car sales, you've got, you know, like a curve. You've got a curve. People will buy cars, you know, it depends on how much money they have, this or that. But then if you look at black cars, they have a slightly higher deviation from the average number. And the amount that deviates, that's called the standard deviation. So that's how you know sometimes if you're looking at something and you say like, oh yeah, black cars are being purchased at a much higher deviation than just standard cars, then you know you might be onto something, and you can kind of look into that and maybe run some studies and see if people will buy more black cars. But when you get into stuff, when you say like rape statistics, there's currently 2 in 1,000 people per year are reporting a crime, and then you get a researcher who says 75% of women are being raped. That's a deviation from the expected standard that is so high that it's actually damaging to your statistic. So that's one big thing to be aware of, is actually there's standard deviation can be good. Standard deviation can also be indicative of a completely failed and irrational study, which a lot of that stuff turns out it is. Also, you get into things like conditional parameters, which conditional parameters are things like the way that you pose your question changes. Like I said, let's go back to the light bulbs. Let's suppose that you ask the question, what's the percent likelihood that you would have these light bulbs that are broken? Like, you've got this sample of 100, and if you're only looking at a sample of 100, what are the odds that 2 of those light bulbs are going to be broken? And or what are the odds that a light bulb is broken? What are the odds that you'll get a broken light bulb? Well, you know that there's 2 broken light bulbs already. I told you that, so the odds are 2 in 100. Now, but when you get into conditional parameters, where you say, like, now let's look at this entire group of 1 million, based on our knowledge that we have 2 broken light bulbs in this sample of 100, what are the odds that, you know, you're going to run into, like, if you just randomly pick another 100 light bulbs, what are the odds that you're going to get 2 more broken light bulbs in that group of 100? Conditional parameters, you see. The way you ask the question, this is very abstract. But basically, if you ask the wrong question, then your statistics can be finding the answer to a problem that has no relevancy to your question at all, or not to the thing that you want to know. So, like, for example, if you ask the question, like, how many... This is one that came up, actually. I was linked to some videos after I ranted on this whole all women are afraid of men thing. Some studies that were being passed around was one that, like, 50% of women suffer head injuries. And what it turned out that was 50% of women out of a sample of women who were abused, and it was actually kind of a broader study. And then it was like they had a bunch of people. It was like how many people in the population tend to be in conflict. Like, it was just abused for any reason, whether they got in a bar fight or if it was a spouse or anything like that. How many of them, out of those people, how many of them suffered head injuries or this or that? It's all kind of, it was all very misleading. It was kind of like not 50% of women suffer head injuries. It was 50% of women out of an isolated sample that was taken specifically for this study, where we already identified people who had suffered trauma as a result of crime. Those people suffered head injuries. We get into weird stuff like that. But a good example, I've talked before about statistics and how they're not really... how they don't always mean what you think they mean. But a good example is the Monty Hall problem. It's very, very popular. I've talked about this one before, actually. The Monty Hall problem is basically this. You have 3 doors, not 2 doors, 3 doors. 2 of them have something terrible behind them, like a beehive, and 1 of them has a brand new car. This comes from a game show, actually. And what they would do is they would let you choose a door, and then after you chose a door, they would reveal one of the wrong doors. Like, they would open up a door and they would show, oh, here's a beehive, lucky you didn't choose that one. And then they would ask, would you like to change your door? And a lot of people would just stick with the same door because they have it in their head. They see they've got 2 doors remaining and they think it's a 50-50 chance. It doesn't matter if I switch or if I stay. Now, The problem is that the human brain doesn't work with numbers very well. So what people were seeing is they were just seeing the two doors and thinking 50-50 because they were asking the wrong question. They were asking themselves, of this sample group I now have, what are the odds that what are the odds that I have the right answer? Their answer was still 1 in 3, because when they first made their choice, they had a 1 in 3 chance of getting the right door. They had a 2 in 3 chance of being wrong. So even though they know that one of the doors is wrong, if they don't switch, they still only have a 1 in 3 chance of being right, because that's how it started with. That's the first condition that they started with. The second condition, which was, should you now switch, is completely isolated. It's separate. And the answer was, yes, you should switch, because the odds were better that you were on the wrong door, and you should switch, because now you're more likely to switch to a correct door. I don't remember the exact number on it turns out what the likelihood of being correct is. But the Monty Hall problem is one of those statistics that's it's just a problem that's very interesting, because it reveals how abstract the entire concept of grabbing numbers and using them for stuff really can be, how all the percentages and everything actually works. So the real thing to take home from this lesson, from all this, is that statistics are very valuable, but if you don't know how to use them, they really are meaningless. I mean, to the average person, they're meaningless. They get reported on in the news all the time. We saw it come up in the global warming debate. Drove me crazy. We saw it come up. We see it come up with feminism. We see it come up with just about anything where people are doing science, and the news can report some of these studies to people. They'll just grab things. Like I say, they'll grab stuff where they say, like, we've got confirmed trauma patients. How many of them had head injuries? And then we'll say, like, oh, 50% of women get head injuries. And it's like, you know, out of a specific group, you've got a confound in your study here. You've got a thing screwed up. Oh, that's right, confounds. I was going to talk about confounds. In every study, you get this thing called a confound. I've talked about this before in the psychology overview video. A confound is when you have an element in your study that you cannot account for. It's something that's affecting your data and you're just not aware of it. Like, for example, if everyone knew what you were studying and they all got together and conspired to ruin your data, that would be a confound. That would be a variable in your data that you didn't account for. It screws up your data. And confounds are very common. They're especially common in statistics, because if you go around and you ask people questions, you say things like, do you agree with this, or do you think this or that? You'll find that people will try and express a view that you want to hear. Like you say, like, do you think that we should raise minimum wage? And you'll find a lot of people say yes, you know, openly. This is a recent poll that I've seen. Is, hey, like 80% of people say yes, and then, you know, yet there's still no raise in minimum wage. Well, there is in a lot of places. Maybe I'm wrong. But anyway, so a lot of people say yes, but let's suppose that they just said yes because they thought that it was altruistic. When it comes time to vote, though, they actually would shoot down the vote if you gave them the chance. And that's only in private. So you get this confound where people want to seem altruistic maybe, but they don't really want to be altruistic. Stuff like that. So that screws up your data. It makes it all mean something totally different. And as I say, that's really the biggest thing of statistics, is actually you'll find that statistics is never, ever, almost ever about drawing a conclusion. It's more about trying to figure out how your numbers are wrong. Almost anytime you see any kind of thing with numbers, with statistics, you should never stop and say, oh, those numbers are right, they must mean something. You should say to yourself, how are those numbers wrong? What's wrong about those numbers? How are they screwed up? How might they be totally and completely, utterly botched beyond all recognition? Because that's what the whole discipline really is more about, is it's just trying to figure out what's accurate and what isn't. So, statistics and probability, we could get a little bit more into the math of it, but that kind of sucks unless you guys want to do factorials. Another way that I could compare it is if you think about dice. Like, for example, if you're rolling one die, you have one six-sided die. What are the odds of rolling a 6? To get like a 6, that's 1 in 6. Well, what are the odds if you roll 2 dice? It's not, you would think that it would be 2 and 6, because now you have 2 dice, you roll them both. You know, 2 and 6. But then if you had 6 dice, that would guarantee that you always roll a 6 every single time, and we know that's not true. Otherwise, Yahtzee wouldn't work at all. You would never be able to do anything besides, like, you would always roll one of every number. So it turns out that you have to actually look at your your data sets and really say, like, what are the odds that you would roll, like if you had 2 dice, what are the odds that one rolls a 1 and one rolls a 6? What are the odds that one rolls a 1 and one rolls, and you get another 1? What's the odds of getting 2 1s? What's the odds of getting 2 2s? What's the odds of this? What's the odds of that? And that's how it all works. So yes, that's why statistical data is very weak when it comes to research, because a lot of times it means nothing. When you get a very broad population, you'll find that there are a lot of confounds, there's a lot of deviations. It's all very broad, and trying to make sense of it is a discipline unto itself. So anytime you hear someone quote a statistic at you to say, like, oh, you know, this is absolutely true, you have to realize that it may bolster the argument, it may sound compelling, but it's not necessarily as accurate as it sounds. It may not really mean anything. What you get into then is, I mentioned, like, the global warming debate, for example. They talk all the time about statistics. This came up. And the problem with that debate was that the global warming thing really doesn't have as much to do with statistics as it does with their model. They're trying to create a model that demonstrates the global warming thing, and actually the chemistry works. The chemistry works for this model that they have. What they're trying to do now is they're trying to figure out how to make the model apply on a global scale. They're trying to figure out, like, how we can do a small scale model, so what happens when you go to a large scale? And so that's where you get into really complicated stuff, where they get into more debate, where they say, like, well, did we account for volcanic activity? Did we account for sun activity? Did we account for contrails produced by airplanes? There's so many variables, and it's hard to figure out. They all contribute to cooling or heating in their own way, and that's what they're really debating, is not whether or not global warming is possible, but to what extent is it occurring, and like, how bad is it? Can we? And they're trying to predict what's going to happen with it on into the future. Now, there are skeptics, of course. There are large business owners who want to shut the whole thing down. But regardless of all that, you have to be able to separate the politics from the science and realize that the main thing is really just they're trying to make the model more accurate. And so scientific skepticism, constructive skepticism should be encouraged, because it will produce a more accurate model. You'll find things like when they say, like, oh, you forgot to account for sun activity, you know. It doesn't destroy the model. It allows them, they might say, oh, yeah, you're right, we didn't account for sun activity. And then they would go in there and they would actually add that to the model. And then they would say something like, oh, it turns out sun activity actually is bad. It catches more sunlight and causes more warming, stuff like that. I don't really know a whole lot about their model. But that's kind of how it actually works. That's how the science really is. So, again, that sort of thing, as you get into this, is it's like we have a stronger correlation between sun activity and heating than we do with this global warming thing than with these emissions. And it's kind of like, well, that may be true, but under our model, like, if we account for that, then it kind of it gets worse. It just makes the situation worse. So you get into that back and forth where it's like the corollary data has no meaning. What really matters is the scientific model and the math involved, and that's what it generally comes down to. Also, too, that's one way that you know that you're in an ideology and not so much a scientist, because if you have a situation where you can't question the data. If a researcher says, like, all women are in danger of being assaulted by men, and you can't question it, and there's really not, like, a model, and there's really nothing you can test, it's sort of an ideological belief more than anything, because there's no way to really examine that data, and that's kind of the charm of it. That's sort of why people latch onto it and they like it. It's something you can't disprove a negative. You can't say that you know, it's like you can't say that there's no such thing as a patriarchy, just like you can't say there's no such thing as Bigfoot or ghosts or things like that. Because if you can't prove, you can't prove there's no evidence of something. If something doesn't exist, there's no evidence that it doesn't exist. That's like, you know, it's like there could be an invisible purple creature that lives in my closet, and it expertly never ever leaves any evidence of its existence. Just because I've never found evidence it doesn't exist. Just because I've never found evidence of it existing doesn't mean it's not there. It's that sort of thing. And you get into that, and then, you know, you can find researchers who will confirm stuff like that, all kinds of things like that. You can find statisticians, I guarantee you, who will confirm the existence of ghosts and Bigfoot if you look for them. You will find this sort of thing for just about any sort of subject that's controversial. Those numbers mean nothing. They never have, and they never will, because there's no way for you to actually examine that data in an empirical setting. Because that's what statistics are really for, is they're just a way, they just direct you towards an answer, and then you send someone who has the proper expertise to actually look at those numbers and do some real research, to really look into things. That's why I say, you look at the corollary data for global warming, and whether it adds to or diminishes the model, what they then do is they look at that data and they add it to the model, or they change the model, or they do whatever it is that needs to be done. That's how it works. It's not an ideological thing. It's not like the corollary data proves or disproves necessarily anything. It's just sort of a place for people to look. If you say you've got a lot of people who ate at a Mexican restaurant and then they got Campylobacter, it doesn't mean that that place needs to be shut down, necessarily. It could just be that it's a really popular joint in town. And that's right, I was going to say, epidemiological studies, I wanted to talk about confounds there. Epidemiological studies are often used sometimes to discover causes for problems, and this can be very damaging because they're not really meant for this. But suppose you didn't know what caused food poisoning, and you thought it was like televisions or something like that. So what you could do then is you could go around and you could talk to everyone who got food poisoning recently, and you would find out that 100% of them had televisions. And then you would report this data. You would go around telling everyone, I've proven that televisions cause food poisoning. I don't know how yet. I haven't done any real research into this subject, but I've discovered that this type of food poisoning is caused by your television. You get people who do that all the time. They've got a drum to beat. They want to prove that televisions are causing all the nation's problems. So that sort of thing you also need to look out for. Again, not a good way to draw data, because what you need to do then is then have a researcher go and get a television and then put it in a room full of a bunch of lab rats and then see if the lab rats get food poisoning. And when they don't, then you report that, oh yeah, this has nothing to do with food poisoning. The real data is empirical. The statistics are just so you can kind of look into stuff. Reverse, like epidemiology, to find a cause for something when you don't know the cause originally tends to be very flaky, even at the best of times. So don't fall for that either. Can I think of anything else that where statistics will fail us? Well, I don't know. I hope that's enough. I hope that's rather direct enough. I meandered a little bit, but mainly because, like I say, talking about the real numbers, getting into standard deviations, it's hard to demonstrate. Except verbally. Like I say, it's all just so abstract, and it involves a lot of calculus and stuff like that. So be aware. I mean, if you went to college and you got a degree in, say, like a sort of like a philosophy thing that has recently gotten popular, like suppose it's a really strong ideology and it's gotten, to be where people believe all these statistics, and your degree didn't include a statistics class, I'm afraid that you didn't major in anything terribly scientific. You majored in philosophy, and the data that you're quoting may or may not be like important to anyone in any way or any form. So yes, that's just numbers for you. They really don't care. They really don't care about your ideology. Numbers are just numbers. They will say what they say. If you get someone who is specifically looking for some kind of cause to support, then you can get them to say very misleading things. But that's how they are. So never look at statistics and say, there it is, that supports my opinion. You've got to actually look at some of the studies that go beyond, and you need good sample sizes. Because if you get a small sample size, like I say, let's go back to rolling dice. Let's suppose, or no, we could use the light bulbs. Let's suppose that we were testing light bulbs and we got one light bulb. We tested one light bulb out of the millions. Well, let's suppose that we got the only broken light bulb in the whole batch, and we screw the thing in, and we test it out, and it goes, and we say, oh, it's broken. Like, well, 100% of my testing sample was broken. If you go and you report that to the company you work for, they will fire you because you are wasting their time. You are an idiot. There's no sense that you can make of that data. You can't go back and say, like, well, there's a certain percent chance of this or that. You don't know. You basically have no way, with only one sample group, you basically have no way of knowing what the numbers mean. There's no way to go back and make sense of that. You can't figure out your deviations very well, really. It's like you would expect a certain number of them to be faulty, and one of them was faulty. So it means nothing. It's worthless. If you have a small sample group, it's worthless. And you get into that, like a study of 20 people. I think I complained about that once. You get into a study of 20 people, and it's like they all report that some kind of cure worked for them. And you find out that, like, not only was there a big confound, but maybe you just got the 20 people out of the 300 million that lived in the world. Maybe all 20 of them participated in your study. What are the odds of that? Seems rather slim, but it can happen. In fact, I once worked for a researcher who we got into this sort of thing. I actually had this kind of problem. We had a confound. I was testing fruit flies. What we were doing is I was trying to get these fruit flies to the goal of the study was to get these fruit flies to select for nicotine, as we were feeding them different kinds of food, and some food had more nicotine in it than others. It was sort of it was like a grape auger sort of thing that they really liked when we didn't, they liked the grape auger. And what we were trying to do is we were trying to get them to lay enough eggs on the severely poisoned nicotine samples that we could actually then collect the eggs and then grow like a species of fruit flies that just love nicotine. This joke that I actually did a joke about this in Fallout New Vegas. But anyway, though, so what happened in the first study was, it looked really promising. We actually got a ton of eggs on all of the different samples, including the nicotine samples. And so we did our numbers, we did our reports on it. We were like, oh yeah, we could go on further with this. We could actually maybe collect some of these things. But then every subsequent study afterward, we wound up not having enough eggs on the nicotine samples to really actually breed another generation of flies. And we couldn't figure out why this was, but I have a theory. My hypothesis on this was that the auger sometimes would bubble, and the bubble would pop, and it would cause a slight deformation in the auger. And I think that what happened was the flies liked to lay their eggs in like depressions in the auger. They wanted them to be protected from the elements, so they would try to lay them down in these little crevices. So what I think happened was that we had more deformations in the first samples than we did in later studies. Peer review basically obliterated this whole plan for the study. It wound up being like something we couldn't do. But that was a confound. That was something that would have, statistically speaking, it was a question of what are the odds that we would be able to repeat this, like what are the odds that we were doing this or doing that. And when you start to get larger sample groups, when you do more studies, and you try to repeat the experiment over and over again, you find that maybe your first experiment had something in it that threw the numbers off, and it's all botched. And so that's why, again, you don't want just a study with like 5-10 people in it. Those are worthless. You don't want to study where they ask leading questions. Those are worthless. You don't want to study where you have any kind of confound at all, or where you're not in control. Those are worthless. And a lot of times in statistics, you don't have any control, and that's why they're not totally worthless, but they can only really direct you to where you need to look next, and they never lead to a conclusion. They just never use statistics to make a conclusion. Use them to make a hypothesis. You can maybe explain why you're seeing certain kinds of numbers, but it doesn't always mean that the numbers clearly indicate what you think they do. So that's it for that, I think. I hope that this works out well. This is one of these things I haven't not asked for. So yeah, so I hope that was clear enough, not too meandering. Like I said, difficult, a little bit more abstract, but yes, but a good number of reasons why you should never use statistics too heavily to support your own arguments, ideas, or beliefs. But anyway, though, I suppose until next time, I will catch you guys later.